I want to give you another quiz. Okay. So I want everybody to write down their best estimate of the stopping time today.
Up to 4?
I don't want to bias your estimates, and then we'll see how well you do. So based on your prior experiences, what do you think the stopping time will be? You don't have to tell me. Just write this down, and you know what you think it will be. Right? So on average, the group should get it correct. Right? Because very large sample size, and there will be some optimistic people and pessimistic people, and on average, it should be about correct. We'll try this experiment. We'll see. We'll see. And since I don't know the results, I can't influence them, right? So, all right. So I next want to talk about how to deal with variable amplitude within multi-axial fatigue, and to talk about some of the things we know and some that we do not. So this is a slide from this morning, and it doesn't really matter whose models you choose. We could have chosen all of the strain models, but when we look at these, then we see either science criteria for the octahedral stress or the shear stress from Finlay's, or essentially the shear stresses from Dang Van. How do we determine that range for a complicated loading cycle? You know, it's easy if I just have tension loads or torsion loads or any kind of combined loads, but for example, how would I do this for a complicated path? And I already showed you that if I were to use the octahedral stress for a 90-degree out-of-phase loading path for science criteria, this would always be 0, right? Because it never changes. That's the reason you build up a 90-degree out-of-phase path. Let's look at how we look at those kinds of problems. And so first thing is when I look at the shear stress and I do calculations, of course, then there are always 2 of them. And if you go back to one of the early slides this morning, I had a cube with all the 6 stresses and strains. Then there are always 2 orthogonal shear stresses, and so I'll just let those be tau A and tau B. And suppose I had a shear stress cycle that looked like that. What would I do for the range? So there are some things that people do, and they say, well, you know, one of the things that I could do is that I could look for the longest chord, and that is I could pick a point on here, and I could search and find the biggest distance away, and that will be delta 2. That will be delta tau, and some people do that. And if you read the literature, then there are all kinds of people who have written, well, but there are ways of fooling this idea of the longest chord. And the way to fool the longest chord idea is to just have something that's kind of a hook-shaped loading path. Other people like to fit an ellipse around things. And you say, well, that's kind of attractive to fit an ellipse. And when I fit an ellipse, I could get a couple of different radiuses. You know, I could measure the ellipticity as well if I wanted. Right? I can say, okay, I have the major axis along here, and I have the minor axis of the ellipse that goes along here. And okay, so there are some variants of this. You know, all kinds of papers like this. And actually, my friends proposed this, and I just showed them there's a small problem with this. There's a small problem with this. Let's do a little experiment. Right? You know I like these thought experiments, right? Suppose I do a tension torsion test, and I plot the tension loads along that axis and the torsion loads along that axis, okay? And I have a real test machine. And if I have a real test machine, it's difficult to control this really to 0. So maybe on the first loading cycle, I have a loading path that looks like this. Okay, and here are the endpoints. Right? Just a little bit of torsion, because that's how the machine really works. And then On the next cycle, of course, it changes a little bit. And maybe on the next cycle, it does okay. Okay, that's the kind of loading history I have. Right? Fine. What's the smallest ellipse you can put around that data? The smallest ellipse you can put around that data is actually a circle. So it predicts that that's just as damaging as a loading history that does this. And it's just nonsense. And so there are all kinds of things in the literature like this. In my opinion, none of them work. They only work for short analytical histories. Pull a little bit, twist a little bit, and things like that. But by and large, these things do not work very well. Okay. Now you can draw a box around it. That helps. That's one of the better ones. And like I say, there's the one I just showed you. So there are all kinds of things in world drawing history. I prefer not to do that. I mean, how would I do it for this? What would I do? Look at only the biggest ellipse and then find some way of sub-ellipses and sub-sub-ellipses and so on and so forth. But there's an awful lot of data, or an awful lot of papers in the literature about doing that. Now, I prefer to think about it in a different way. So there's the crankshaft I showed earlier, and that's the real kinds of loads that you get. And I prefer to look at things in this, and then say, if I have a history like that, how might I define cycles? And if I just look visually at this, then I can see that I have this big bending cycle in here, and I have some torsional subcycles that are in here. And I can imagine calculating some fatigue damage for this. By the way, this is going to damage one plane, and this stuff is going to damage some other plane in the material, and they will not interact with one another. So doing something like combining all of this into one big cycle with an ellipse, the way I fit an ellipse around this, it would probably look something way like this. And so I would seriously overestimate the bending amplitude. So you can see all those problems. So I think we should do something different. And so we should follow what we do in uniaxial fatigue. And so if you have uniaxial fatigue, I think everybody in the world uses some variant of rainflow counting. And rainflow counting comes from the Japanese. References on the bottom. I suspect most people haven't actually read the paper. I mentioned yesterday, I think that all the tests were done in torsion, not in tension, because that's what Endo likes to do, or like to do. Rainflow, kind of interesting. It's very unusual in the Japanese literature to see the graduate student's name first. And of course the graduate student did the work. And rainflow counting is one paragraph of this graduate student's master's thesis. One paragraph. And interesting. The master's thesis at that time was reproduced on blueprint paper. So I have a copy of his master's thesis, reproduced on blueprint paper, written in English. Not very good English, okay, but written in English. And the first pages of the master's thesis, maybe 20 pages or so on, are a long, convoluted set of rules and arguments and things which are incomprehensible, I think, in any language. But that's what the professor demanded. Because the professor had these complex ideas and so on and so forth. And what Natsushi wrote then in this paragraph, he said, and as an afterthought, and here's an alternative method which is easier to explain. And he said, okay, orient the history so that it resembles a pagoda. Okay, so there's my loading history in blue, and I orient it so that it resembles a pagoda, and you can see that, okay, that's what it looks like. Okay, fine. Pretty good instructions from Japanese to English, right? Orient it so it resembles a pagoda. And then imagine that it rains on the pagoda. Okay, what happens when it rains on the pagoda? So rain starts up here on the top, and of course rain is here, and it falls, and of course rain drops over the edge and picks up on this roof and drops over the edge and sooner or later hits the ground. And from where rain starts until rain stops, that's 1/2 of a cycle. And then you can imagine a pagoda, they're kind of light, airy structures, and maybe on a windy day, then water can flow inside as well. There's no problem with that. Or maybe the roof leaks. Imagine whatever you need to. And rain starts here, and now rain falls off the end. But now we impose one of his rules, and the rule is, well, this rain must stop because it encountered a peak over here that was more negative than where it started. So rain can't go back on itself. Fine. And the third rule, right? Third rule is, right? Rain starts here because rain has to fall on all parts of the roof. Rain starts here, and now rain stops because it hits rain from above. And every time rain starts and stops, it defines 1/2 of the cycle. And that was the original presentation, and that's how it got its name, rainflow. Now, you might wonder why everyone in the world uses this method for doing variable amplitude when it has this background. Because what is the justification for this? Right? It certainly cannot be rain falling on the roof, but it's kind of a colorful way of describing this. So let's look at this same loading history in a little bit different view. Okay. So there's the same loading history as before. Okay. You can imagine rain falling off the roof and so on if you like. So rain will start at A and end at D, and that's 1/2 of a cycle, and rain will start on the inside, and rain will drip here, and drip off here, and drip off here, and that's the other half of the cycle, and so on and so forth. But underneath this, with the plasticity exaggerated, just for the example, I plot out the materials deformation. And now, if I show you the bottom picture, and I ask you, where are the cycles? It's easy, isn't it? So you look at this bottom picture and you say, okay, here's what I see. What I see is I see one big cycle here. And then I see A to D to I. And then I say, you know, there's another big cycle, and there's another big cycle in here. There's another big one. B to C, back to here. And I see a couple of small things. I see this. Right? I see this thing in here. And of course, I see this little thing in here. And it's not that thing. So if I show you this view, then the identification of the cycles becomes easy. Right? And so you can see what's being identified is the idea of closed hysteresis loops. Right? And that's the concept. I say everybody uses it. There are some small variants of it, but as I've alluded to many times, these small variants of rainflow are driven by people's need to write papers and go to conferences rather than being substantially different. I hold my hand up as a member of that club. I have 2 or 3 papers on rainflow which are not substantially different either. That explains how to do that. So I'm a sinner who can cast the first stone. That's why I know the technique. Okay. All right. So that's the background. You know, today we don't use any of those silly rules. We do it really easily, right? And when I look at the rainflow counting routines that I use and put in little boxes, then I have only 3 or 4 lines of computer code. Yeah, it's pretty easy. Right? I'll just show you how to rainflow count. Just compare the ranges. Right? I look at the magnitude of the range going from A to B. Okay? I have nothing to compare it to. So go to the next range. So now I have the magnitude of the range B and C and I compare the magnitude of the range B and C, and I compare it to the magnitude of the range before it. And since this magnitude is smaller than the one before it, do nothing. Okay? And now I compare the magnitude of C to D, and the magnitude of C to D is bigger than the one before it, B to C. Rule number 3, count B to C as a cycle. I'm done. Those are the only 3 rules. First start rule, right? You got to have 2 ranges, and the range is either bigger or smaller. And of course, equal is possible, but equal is just as good as bigger. So now, since I counted B and C as a cycle, take it out of the history, and so the new comparison range goes between A and D. So I've just identified that. And then I say, okay, fine. D to E is less than A to D, do nothing. E to F is less than D to E, do nothing. F to G is bigger than E to F. Take this out and make it a cycle. So now I have a cycle from A to D and from D to G. That one's smaller, do nothing. That one is bigger. Take this out. And now I'm left with the cycle from A to D and from D to I. They're the same. Take them out. And I'm done. And I'm done. And that's the way all the little data recorders work. And so you can now buy little rainflow boxes that are the size of a small package of matches, right? And they work really quickly, right? So that's how it's done. Now, how about the physical insight? Right? Well, let's just look at what happens in going from D to I. So I'm going from here to here. And there's a major cycle in going from here to here, but at this point, this major cycle is interrupted a little bit, in that this event interrupts the major load cycle going from here to here. And so take this little cycle out. Count the damage for it, count the strain ranges, count whatever, normal stresses, normal strains, and do all that stuff. But take it out. We take out the damaging content. And then I continue to deform along this way. And when I do that, this is a little interruption in here, and so I have that interruption, right? Take it out, count the damage, and I'm left with the overall cycles. And that's the ideas behind all this, right? And it works for crack growth, and it works for the stress life approach and strain life approach. And I say everybody uses it. Everybody uses it because it correctly assesses where the cycles are. All right. So let's use this now and think about this in terms of multi-axial fatigue. And this is another one that I did yesterday. And said, okay, if we think about now, and I just want to use one of the principal stress models, I just want to rainflow count the principal stresses. And so if I look at the first principal stress, right, this is the loading history like that, and I look at the first principal stress, then of course it peaks up there and then becomes 0. So if I try to use principal stress in the loading history, right, it's a bad idea. It's a bad idea. And the reason being, of course, is in my simple tension and compression test, then we know that during the second half of the loading cycle, when I press that in compression, sigma 3 has magnitude. But I'm not counting the channel sigma 3, right? I can rainflow count or do whatever counting I like on only one of the channels. And so this is a problem. So no one can use principal stresses, so you need something else. And so people have introduced the concept of assigned equivalent stress to solve this problem. Right? What is assigned equivalent stress? It says, fine, let's calculate the equivalent stress, right? Like this. And then let's use the sign of the largest magnitude. So if the largest principal stress has a bigger is in compression, but I take the absolute value, then you can see sigma 3 will solve my problem. So what I will get is I will get this. Okay, there's sigma 1, there's sigma 3, and there's what the signed equivalent stress does, exactly what I want. So it says if I have a variable amplitude loading history, I could simply calculate the signed equivalent stress, right? and then I could rainflow count it and get all of the cycles. And by the way, if I rainflow counted it, I could also rainflow count the shear stresses if I wished. Right? There's no problem in rainflow counting sigma 1 minus sigma 2, and there's no problem in knowing what the normal stresses are for that. So I could apply any of the models. The idea is that if you have variable amplitude loading, what is the master signal you want to count? If I want to count shear strains, how would I do that? Okay. All right, so fine, that works. Yeah, until you try real data. Right? By the way, there's what happens in torsion now. So in torsion, I have sigma 3 that looks like this, and sigma 1 that looks like that. So if you apply signed equivalent stress to torsion, you end up with 2 load cycles. So there are some difficulties. By the way, if you go to work and buy the commercial packages, you either can buy FE Safe or you can buy N-codes, whatever it is, FE Life these days. This is exactly what they do. And they say, factor 2 is no big problem. I don't know. I don't know. I'd ask for a discount because you know the answer. Okay. Suppose I had these torsional stresses though, right? And I can draw these nice, perfect stresses like that. But suppose I had some real data. And here's what real data looks like. Right? This is not an artifact in the screen, but the real data is really wiggly like that, right? And for pure torsion, this one should be exactly equal to that one. But for real data, sometimes this one is going to be a little bit higher, and sometimes this one is going to be a little bit higher, and sometimes this one is going to be a little bit higher, and so on. Right? So let's calculate the signed equivalent stress. And that's what it looks like. Remember, this is one torsion cycle that I now managed to turn into, well, how many ever is there, right? Maybe 50 cycles of variable magnitude. So these ideas are things that people do, and they are shortcuts that unfortunately have found their way into all the commercial codes that are pretty dangerous on real data. They're really nice on analytical data that goes from this point to this point. Just like these ideas of the maximum circumscribed ellipse and all that kind of stuff. Those are really nice on data that's analytic that goes from point to point. But when you have real data that's got a bit of variability in it, pretty awful stuff. Pretty awful stuff. So I don't like to use any of these. I think they can be dangerous. So what I think you should do is I think you should just use the idea of rainflow counting on a plane. And so here's another one of these box type histories. So you can see there's the box history we looked at before, the square history, and then we just put in some interruptions that look like that. 4 of them. And of course, if you look at that, you immediately can find the cycle and say, okay, what I see in here is I see this one big cycle, and if you use my description of the rainflow process, as the rainflow process separates out the overall loading pattern from the little interruptions or subcycles. Right? That's what rainflow does physically. Right? Well, where's the overall loading cycle and where are the interruptions? Right? It's pretty clear where they are. And if you don't want to work in terms of the strains, here is the corresponding stress history for that, in terms of shear stress and axial stress. And again, I see the same thing, right? I say, well, okay, like that. I have this box that corresponds to the overall box, and I have these small subcycles which are here. By the way, just as a note of plasticity, if I were to traverse the box in the opposite direction, around this way, clockwise rather than counterclockwise, then the stress response box would go from being tilted this way to tilted over that way. Okay, so you'll see it. And that's why we need to know about the sign of the shear stress. But now let's just start to look at other planes. And so here's the stress and strain on the 0 degree plane. And it represents both the shear stress on the right side and the tension stress on the other side. And now if I look at that history, and again, I see what's here. And I can choose either to say, fine, I want to work with the principal stress, all right, or I want to work with the principal shear stress, either one. I have, and in either case, I say, okay, here's an interruption, here's one, and here's one. So on. And then I can keep doing this. Here's what it looks like on other planes, on the 30-degree plane and the 60-degree plane, and there's what it looks like on the 120 and 150-degree plane. So for those of you who are used to looking at fatigue hysteresis loops, you will see that in multi-axial loading they can have kind of interesting and strange shapes. There's no reason a hysteresis loop has to be closed. By the way, if you go back through these last slides, right? So I'll let you look at these two for a moment, and I will go back to the last one. And so there's the last one, right? What's the critical plane? Which one has the most damage? So when you get a picture of this, then you can see, well, okay, here's the strain range, and so strain range a little bit more than 003, and here's the stress range, and I don't know, it looks like the stress range is maybe a couple of hundred. Right. And if you look at this one, right, 150-degree plane, you can say, well, okay, strain range is the same, about 0.003 to this one, and of course then we look at what the stresses are, and you say, oh, here the stresses are 250, so this will be a more damaging plane than the other one. And of course, this is just something visually we can do in the lecture. If we were to do this, of course, we would do the calculations, and we would calculate shears and normals and all that kind of stuff. But these are kind of useful just in the class, just to get an idea of what the process is. And so the process would be to go through the different planes and calculate fatigue damage for the major cycles and subcycles on these different planes. By the way, if you look at the preceding one, the 150-degree plane, which is the critical plane, and you look at the shear strain history, there's what it looks like. And now it looks a little bit more like uniaxial loading and something you're familiar with, and that you can see that it's an overall cycle that's going from here to here, and there are some subcycles which exist. All right. So this is not the only way to do it. So there's another cycle counting method, and it's the Wang and Brown method. And the Wang and Brown method is used in a lot of the software. And it's kind of odd that people use it. You know, I told you if you have a 90-degree out-of-phase path, that the equivalent strain is constant. So that means I can't count equivalent strain or equivalent stress. But it would be very convenient if I could take all loading histories and reduce any loading history. You know, presumably if you had an analytical solution, you could have 6 stresses and 6 strains, and I'd like to reduce that to only one channel of loading history that I could use to identify cycles. And the way to do that, of course, is with equivalent stress. So here are a loading history in time of the axial strains and also the shear loads. And if I plot the axial strain and shear strain versus one another, I get a loading history like that. And if I ask you where are the cycles in that picture, you will not a clue, right? Not a clue where the individual cycles are. So how do you proceed? How do you proceed through this? Well, Wang, of course, the graduate student realized that I could count equivalent strain if I offset the equivalent strain so that equivalent strain is always positive. So why not add a fictitious strain to all the real strains so that the equivalent strain is only in one direction? So remember, our problem with the equivalent strain is we don't know how to differentiate between positive and negative very well. So let's just add a big offset. So that's exactly what he said. He said, okay, what offset should you add? Well, the best offset to add is, let's look at the loading history and let's figure out what is the maximum value of the equivalent strain. So let's start here and then add that to all the different ones. And so if I do that, or subtract it rather from all the different ones. So if I subtract the strain here from all the different ones, this always starts at 0, and I'm subtracting something from all the other ones, and you will get an equivalent strain history that looks like this. And now, I essentially just rainfall count this. And if I rainfall count this, I get this portion of the cycle A to B, and then I jump over here. So remember about rain falling off pagoda roofs, and I come over to this part of the cycle, and then I go here, and that defines 1/2 of the cycle. And if you look at what that does physically, that's a loading, that takes this part of the cycle and pairs it with this part of the cycle. Okay, that's the biggest one. That's the biggest one. And kind of funny, you know, Brown and Miller were the originators of thinking about a critical plane. And if you look at what that says, this kind of counting method says we have a critical planes. We have half the cycle with one critical plane, more than half in this example, but we have part of the cycle with this critical plane and another part of the cycle with this critical plane. But that's dealt with by not talking about it in their papers. But it's a fundamental problem in concept. Okay, so that's how it's done. And then you do the next one. So I already counted, just like in rainflow counting, I counted from here to here to here. So now count the next part. And basically, if I go back into the loading history, I want to deal with this part in the middle because I haven't done this yet. So again, I start with this as the reference point, and then I calculate a new equivalent strain for all this kind of stuff by subtracting this value from it. And if I do that, I get that. And now I do the process again, and I say, okay, I let rain flow on this and drop off here and drop off. And so this part from B to D and this little part here, for E, that defines another half of the cycle. And so you can see what happens. It does this, right? And then it adds in this little part over here. Right? Pretty strange, isn't it? Not a whole lot of logic for this. You wonder why it's used. But, okay. There are a few problems with it. I just showed you how it works, right? But I said it's in all the commercial codes. It's in all the commercial codes because it runs a little faster. So let's do a cycle of tension followed by a cycle of torsion. Cycle of tension followed by a cycle of torsion. And what this method is doing is essentially establishing a reference and then going out in equivalent strain. And so you can think of a vector that starts here and traverses the loading path, and then when I get here, then the loading path goes this, and you can see this vector is getting longer and longer and longer, and it's to this point. And now when it reaches point 2, and so what I've done is simply a cycle of torsion by a cycle of tension. And now as this goes in the opposite direction, during this portion of the unloading, you can see this vector is getting smaller, so you do nothing. Okay, that's equivalent to letting rain drop off the roof, and that's why you have these troughs in the previous pictures. And then I've done part of the torsion cycle, I've counted part of the tension cycle as damaging, and now I load up this way, and nothing happens. And now, if I swing an arc for this, I finish the cycle by adding this part onto the end. And so I've pretty artificially broken up one tension cycle followed by one torsion cycle into some kind of funny half tension, half torsion cycle that doesn't occur in reality. And then I expect to get the right answer. And then for the second reversal, you add this part of the tension cycle with this part of the torsion cycle. And for the third one is a mirror image of this. You add this one and add this one. And for the fourth one, you add this and this. So I have one cycle of tension followed by one cycle of torsion. One cycle of tension followed by one cycle of torsion that I then broke up into some kind of bigger cycle here, little small cycle in here, bigger cycle here, and a little small cycle there. But I had only one cycle of tension and one cycle of torsion. I I don't know. But as I said, it is the most common cycle counting scheme. It is the most cycle counting scheme. Why is that? Well, as I told you, the commercial software vendors use it, and they use it because it's easy for them to compute. It's more difficult to count the rainfall counting on planes if you don't know how to do it. By the way, there are some problems with this. You can easily dream up histories for which it misses the major loading cycle. Suppose I have a major loading cycle that just looks like this. Pretty simple in tension torsion to have something that looks like that. And if I want to know the biggest range, of course the biggest range starts here and goes here. Right? It just traverses around the path. That has to be the biggest range and the most damaging range. And let's look and see what these cycle counting schemes do. Okay, it says start at the maximum, and so when I calculate the equivalent, maybe the maximum turns out to be right at that spot. Right? It's the biggest difference in equivalent strain. So that's the starting spot. And from that starting spot, then I will calculate and I will say, okay, this is half of the cycle. Right there. And then this becomes the starting cycle. And that's this part of the cycle. This becomes a starting point, and this becomes part of the cycle. So I've turned one closed path into three closed paths with a smaller magnitude. I like to try it on my little star histories. Because I was convinced that this history would give you results which were not sensible. And so this is the history that I talked about before. So I talk about this history, 360 little subcycles, every time I move the phase so that I just move around here 1 degree at a time, right, like that. And then I look at this one, and this one I load here, and I load out in this direction. So this distance is the same as this distance. And of course, I was convinced that this would be incredibly damaging compared to this. Because just look at those pictures. Right? The picture on the right has twice the amplitude and ranges, doesn't it? Because if I think about the tension test, this half of the tension test is reversed a little bit later on with the second half of the tension cycle. So a tension cycle goes from here to here. We do some other stuff in between, and then we reverse the other part of the tension cycle. Interesting. There's what the histories look like for the axial loading channel. And oh, something interesting happens, right? You can see that I have all these little cycles, and the real difference between those two histories is the one history has one really big cycle, and lots of little ones, just like this one. Okay. And there's what the other variable phase ones. I showed this before when I was talking about non-proportional hardening. And there's the other, right? And there's the hardening, and so we calculate all the stresses and strains and so on, and I want to know the fatigue cycles. And so I took this loading history, and I calculated what all of the fatigue cycles are. And I used the Wang and Brown method, and I used the rainfall method, and right? Of course, what you find in rainflow, in one case there are 360 smaller cycles. In the case of the second history, the big star, there's one big cycle and 359 smaller ones. And in rainflow counting, of course, the smaller cycles will all have a different magnitude. They'll get smaller and smaller, and of course these have a very small magnitude and these have a bigger one, and so on. And much to my surprise, that's the difference in the histories. What you find out is that all the methods converge and give about the same answer. And that's why they're used, right? It's easy for anyone to come up here and to draw little histories that fool the system, but when you start to get lots of cycles, all the methods seem to work pretty well. This is the incremental path, and of course the difference between Wang and Brown, you get a few more bigger ones, but you don't get any littler ones. And if you rainfall count on the critical plane, you don't get quite as many bigger ones, but you get a lot more smaller ones, and so you just have a higher magnitude of these things that do damage. And if you look at the random path, right, I didn't show that, but the random path, you identify the big ones and about the same number and all the small ones and so on. So after doing these experiments, I concluded that counting the cycles is not an important problem. Any reasonable method will work, and even some of the unreasonable ones. Right? So that doesn't seem to be a problem. Right? By the way, you can do all kinds of interesting things. You can look at these random paths and look at the track observations. And so even though you have everything in random directions, when you look at what happens, there is a plane that finds the critical damage. You do repeat tests of this, and the tracks are always in the same direction. Right? Again, confirming the ideas that we have been talking about today. Even if you have a really complex loading history, there is a plane that sees the most damage. Right? You never find multiple tracks off in all kinds of directions. Anyway, we can find all of those planes for it. So I just show this for the nomenclature. And so here is a plane, and I just label this plane T0. These are the normal stresses that act on a plane at whatever the angle theta is. And there's an A0 plane. That's the in-plane shear stress that acts on the same plane. And then there's an out-of-plane shear stress that acts on a plane going 45 degrees into the surface as you change theta. And there's also an in-plane shear stress on the same plane. And so that's just the nomenclature, tau 0, A0, and A45, and B45. And if you then look at the damage that is calculated on all the different planes, then you look at the damage on all the different planes, then this is the damage. And so you can see that there is always a minimum somewhere in these curves. Right? And that minimum is what's computed as the fatigue life, because that is the plane that will see the most damage, and it corresponds very well with all those kinds of crack observations. And you can see some planes just never see damage, and some of the never see damage, and that's because on this particular plane the shear stresses are always zero. They're always zero. So the ideas work, and they work very well. By the way, there's predicting all of that data. It doesn't matter who's. I claim both of those are the same. So what are the problems in dealing with variable amplitude loading? Well, they're hidden ones, right? So this is one of the hysteresis loops from outer phase loading. Let's take my shear model. I have maximum shear stress over strain, right? We don't care. Right? And we think that the normal stress has an influence, and so all day today I've been opening up my hands to simulate a crack about the normal stress. Suppose we have an outer phase load, like these, and I define the normal stress. Here is the hysteresis loop. Okay? It starts here. And it loads, and this is the end of the loading cycle, and it starts here, and it unloads like this, and then there's interaction on the plasticity, and the stresses actually drop and come back to here. So when I do the calculations, what stress should I use? If I think about the point in time when I have the maximum shear stress, and I look at the normal stress, the maximum shear stress is applied at the time the normal stress is here. Should I take that normal stress? Or should I take the maximum normal stress in the hysteresis loop? What is correct? So it says is that I'm shearing this, right? And while I'm shearing this, there's a really high stress, but I'm not finished shearing it yet. And now I continue shearing it a little bit more, and the stress drops off, such that at the point in time of the maximum shear stress, the normal stress opening the crack is less than it was at a point in time when the shear stress was lower. Okay, that's the issue. Right? What should you do? Right? No one knows, right? No one had experiment. And you can say from this, you say, well, right, let's always be safe, and let's just take the maximum. Okay, fine. Right? And you can say, look at this example. There's not too much difference between the maximum and this one. Okay? How about this one? So along this axis I have the shear, in this case the shear strain, and along this axis I have the normal strain, and so I want to compute the fatigue damage for this, and if I compute the fatigue damage for this, then okay, I will count this, but of course now you sitting there, you can count this, and you can say, okay, fine, here's a little sub-cycle, and here's a few of them like that, and here's one big overall loading cycle that looks like that. And now I just ask the same question. Okay, I'm shearing this, right? And I said earlier that if I can open the crack at the same time, but by the way, when I'm at this point in the shear stress, right, maximum point in the cycle, there's no normal stress at all. And so I can think about, right, my arguments about friction and so on. There is a maximum normal stress, but it happens way back here, right? Way back here. So you have trouble about how do you actually define the damage models. So the problem in variable amplitude loading is in using the damage models that were developed for constant amplitude loading. I have one more, right, that I will use. Suppose I had a torsion cycle. Suppose I had a torsion cycle and I twist this clockwise, and then I untwist it back to 0 and stop. And then I load this in tension a little bit, and then I unload it, stop. And now I finish the torsion cycle by twisting in the other direction. And that's exactly what I've done here. I load this in torsion, I come back and I stop. And then on this plane, right, I introduce a normal stress like that, and then I continue the torsion stress like this and unload that. Would this have any effect? Probably not. What difference does it make if I apply a little tension cycle when there's no shear on it at all? Right? So if I always say, I just want to be conservative, just take the maximum normal stress that ever happened, you can see it falls down completely. It just falls down completely. And this is the problem with one of these star shapes. This is actually a plot of the shear strain and normal stress for the path with 15 different star shapes in it. And you can see what happens. I could choose any normal stress I wanted. Maybe this one that matches this, or this one, or this one, or this one. And this is the real problem in variable amplitude loading. The real problem in variable amplitude loading is interpreting our constant amplitude damage models that we have from very simple little loading histories. It's not the fact of how to count cycles or identify those, but there's almost no work in this area. Almost none. Almost none. Okay? But I want to, right? That doesn't stop people from using these things. And so I will just show you what's done in industry. Then this is a motor frame carrier, engine for goes into the frame, and they want to make a prediction of the fatigue life. And so despite our knowledge lapses that I have pointed out, here's an analysis that has 16 channels, 20,000 elements, and they make a prediction of the fatigue life. By the way, that takes those 20,000 elements run through a loading history that's a few hours long for it, and they calculate everything based on these critical plane models that we have been talking about today, and they just rank order the most damaging element, next damaging element, and so on. And so we believe this is we believe that this is the correct answer. And you compare this to just putting your blinders on and just running a uniaxial analysis on all the different points. And if you were to run a uniaxial analysis on all the different points, this is what you would predict for the fatigue lives. And And the first thing you notice is that you would predict, right, a large number of failure locations that aren't really there. That aren't really there. Right? So this means that if you actually tried a very simple analysis, the designers would spend a whole lot of time trying to fix these failure locations in that complicated structure. In fact, they would spend all their time trying to fix these because this one is a lower life. Right? And the reason being is if you look at a car that's driving around, every load cycle does not damage the same part in the structure. And all the different times in the loading cycle damage other parts of the structure. And what people are looking for now is they are looking, of course, for more accurate and more efficient ways to process these very long time frames. Okay? Hours and hours worth of data through finite element modeling with hundreds of thousands of degrees of freedom. And so that's a good research project. Let me just summarize about how to deal with the whole problem of making an estimate of the Teaglite. So, you know, it's really just computationally intensive, but not conceptually other than the damage models. Right? We start with the loads and strain histories, right? And then we have to run that through a cyclic plasticity model, right? We chew up lots and lots of computer time. And now we have all the stresses and strains in an orthogonal coordinate system. And then we transform all those stresses and strains into what the critical, in the stresses and strains on other planes, and then we search for the critical plane. It's not unusual to have the fatigue software run for a couple of days. Not unusual for a couple of days. But conceptually, it's not difficult. Conceptually, it's not difficult. And there are these few problems that, well, you know, people are, if you just wave your hand, well, you know, we'll get about the right answer. And think, well, it's about the right normal stress, and at least we'll be conservative. So okay. So now I am tired. And I am finished talking because I am very tired. So I want to know what is the consensus of the class of when I would finish, right? Anybody before 5:15 on their note? Oh, what did you write? 4:30, 15 minutes. Okay. Anybody at 6? Not a one. That's never a good bet with me. About 6.
You got another beer tonight.
What?
You got another beer for tonight.
I have another beer. Okay, I am tired really from talking all day, and I know you are tired, particularly in listening to English for the entire day. So I assume no one will complain if I stop now. Everyone who wants to complain I'm stopping too early, raise their hand. No hands. Okay, great. So I will see you in the morning at 9 o'clock tomorrow.